My name is Scott Wolff, and WR Meadows is a privately held organization. We're celebrating our centennial here in about 2 more years. We do have about 14 facilities in North America. We do market globally, I always like to mention. So if there are any projects outside the North American continent, by all means, get in touch. A Meadows family of products include, of course, air barriers, concrete cures, construction liquids, hardeners, densifiers, joint sealants, and our Division 7 products, which we'll talk about the products today: waterproofing, underslab, blindside systems, below grade vapor retarders, aka vapor barriers, hot, cold, and self-curing sheet waterproofing, all of which factor into today's program. Let's begin. Got a lot of stuff to cover, and let's go. So today's objectives will be to discuss the mechanics of how moisture moves through structures or onto structures and the resulting effects to said structures. We'll also explain some of the problems related to deterioration of concrete as a result of, frankly, water exposure. We'll go through some definitions of dampproofing, waterproofing, and vaporproofing, where each are considered or ought to be considered for use, as well as look at the differences between positive and negative side waterproofing. And then the last portion of the session here will be to review a lot of the different products, all these different systems, and certainly where each are best suited based on project site conditions. So we begin with the moisture transportation methods, referred to as the hydrologic cycle. Gravity is certainly what it is, and as we move to moisture movement, capillarity is that action of water transfer, bulk water transfer through capillary means, where two intimate surfaces are in intimate contact with each other. Water can actually defy gravity and traverse upwards laterally. I've seen great examples of capillary water action in certainly above grade wall sections, for example, where entire steel framing had been virtually rusted out. So it's certainly something to be considered. We always want to break that capillary action, and typically we can achieve this through the use of a drainage mat, which we'll discuss also in this program. Diffusion of water vapor in the form of a gas is, in my opinion, probably less of a concern. It's certainly not anything that we don't want to dismiss altogether, but I think some tend to get a little bit super focused on this. But to me, the biggest enemy of moisture transport is bulk air transport. So frankly, I refer to air transport as frankly a hole in the wall, or the failure to properly flash any of the penetrations or rough openings. And dew point is something that also I think is probably sort of akin to diffusion with regards to how moisture gets into or out of a structure. And the dew point typically occurs at, around, or generally within the primary thermal layer. And if we place all of our thermal layer, our insulation, on the outside of the foundation or the above grade wall sections in the form of a closed cell foam plastic, the dew point's generally going to occur largely, always say largely, within the primary thermal layer. And if it's this type of closed cell foam plastic, which has typically a finite amount of water absorption by volume, the pink and the blue stuff, usually by manufacturers of this material, to usually not be much more than, I believe it's like 0.1% by volume. That's expressed as a maximum. So the dew point, again, if anybody's probably, I suspect a lot of people probably watching have been involved in hydrothermal analyses, and the dew point never occurs in a fixed static straight line. It's usually oscillating back and forth, but largely within the thermal layer. And if we place all that on the outboard side of our structures, that's where the majority of the moisture is going to occur, which is certainly where we want to keep it. So how does moisture enter our structures? Bulk water, naturally and not surprisingly. Poor installation. The second bullet point here is the water table. First question I always ask when getting involved in, what type of protection I want to have for my structure is, has a geotechnical soils report, aka a bore test, been performed on the project site prior to production start? Because we always want to determine where the groundwater is relative to the lowest point of the foundation. So if our geotechnical soils report suggests that our bores find water at, say, 57 feet in one hole, another at 63 feet, another at, say, 75 feet, and the bottom portion of our foundation resides at maybe 21 feet. That's pretty indicative that we have quite low groundwater, and that certainly will help drive the type and choice of foundation protection. Site drainage, this is something that is also very, very important, and frankly, something I think that tends to ride under the radar. We always want to make sure that the grades are always sloping away from a structure. If it's inevitable that the grades are flat or even slightly sloped towards a structure, it's not an ideal scenario. It can be dealt with, but it's something that can produce pretty dramatic results, as we will soon see here. Cracks in the foundation, incorrect details, these are all conditions that might lead to how moisture enters a structure. Hydrostatic pressure, defined as the force exerted from the weight of liquid. Its value is directly proportional to the height and density of the liquid, and certainly increases in proportion relative to the depth measured from the surface due to the ever-increasing weight of the fluid exerting a downward force. Capillarity is the force resulting from greater adhesion of a liquid, i.e. water, to a solid surface than the internal cohesion of that liquid. As I mentioned earlier, it allows liquid to rise along vertical surfaces and seemingly defies gravity. So the smaller the diameter, the greater the rise. And my kitschy little example analogy of this is the science experiment likely many of us had in grade school, where we took 2 plates of glass and put them into a bucket of water, and we can actually see how the water is drawn up the 2 intimately locked materials, these i.e. solid surfaces. You know, people doing stuff in the kitchen, if you take the Pyrex beaker, fill it with a liquid, if you look at around the edges, you can actually see how the liquid will actually seemingly draw up the sides of the beaker. So other moisture entering structural elements, water vapor, as we talked about, horizontal and vertical diffusion. And when we look at below grade concrete structures, we have to be of the mindset that concrete is not a true vapor retarder, aka vapor barrier. Whenever we build below grade structures, we should always consider that the soil is should constitute basically 100% relative humidity RH moisture source. And if we consider northern areas like Minnesota, if I last recall, has a 96-inch frost depth per the code, which is obviously 8 feet. Inevitably, we're going to create a usable, viable space below grade, and of course, that's going to be conditioned. So if we're dehumidifying much of the year because we're constantly battling the available moisture underneath the slab, you know, if we're going to condition it to say 30%, 35% RH, and we have 100% RH on all 5 sides, the vertical foundation underslab conditions, we're going to have vapor drive. Now, concrete can certainly be specified to achieve, and when properly placed, can achieve a reasonably low water vapor permeance. That's likely the exception rather than the rules. So inevitably, we want to certainly protect those sides of the concrete that are in intimate contact with this available moisture source. Vapor diffusion is the transmission of water vapor, pardon me, in the form of a gas via vapor pressure delta between 2 sides of a structure. So depending on the differences in temperature and relative humidity from outside to inside, again, this is, you know, if we have 80, 90, 100% RH outside, and we are always conditioning the building's interior to a lower relative humidity, that vapor drive always wants to seek its equilibrium. So high vapor pressure always seeks lower vapor pressure, certainly. Limitations of concrete. Pardon me. Although it's very durable, concrete will eventually deteriorate from natural weathering, and the degree of deterioration is dependent upon the exposure to the most abundant solvent on our planet, which of course is water, temperature fluctuations, aggressive chemicals in soils, inadequate mix and design materials selection in the concrete batch plant, inadequate design for deterioration, such as waterproofing, poor construction practices. So Permeability is defined as the ease of which fluids flow through a material. Trapped air pockets from pore consolidation, i.e. vibrating of concrete, increases that permeability. Voids created due to pore mixing, the age of concrete, finer grades of cement particles, all lead to higher permeability. And concrete obviously never remains ideal over its service life, and likely may increase this permeability over time. Certainly, this never happens, and we never see this on projects. So porosity is defined as the ratio of volumes of openings or voids to the total volume of material. Most of important factor when placing concrete, of course, is the water to cement ratio. When we refer to pouring of concrete, as one prominent building science individual mentioned, that is very suggestive to a higher water to cement ratio. Higher water to cement creates a more porous concrete and certainly a weaker concrete. The inverse of that, a lower water to cement ratio, typically will produce a lower porosity of concrete, and certainly a stronger concrete. So when we refer to putting concrete down, we refer to it in ACI terms. We're placing concrete or casting concrete. So we tend to be concrete snobs when in this industry. So controlling moisture, of course, is key to obviously building function, longevity, occupant health and safety, maintaining optimum mechanical operation, and certainly lower energy costs. We certainly want to protect the building from damage. We all know that the structure takes the most prominence when designing a building, so we're obviously in the business to protect the structure, I think, as Isaac even mentioned at the top. Important elements for moisture control, we want to make sure that they're continuous, that they're all of the connections, the foundation connections are made to the above grade air barrier connection in a fully adhered manner. They need to be obviously durable, resilient, compliant. And what I mean by these last 2 points are that, buildings move, perhaps maybe less so below grade, but we do want to consider using materials that have an elastomeric or flexible property to it. Of course, they do have their limitations, but certainly below grade, unless we're applying, our foundations or setting our foundations on disturbed soil, that's the worst case scenario. We're not likely going to experience much movement, but we certainly want to have that capability incorporated. Factors influencing effectiveness, of course, obviously design, materials, workmanship, QA are all part of it. So, I always like to suggest in any of these PowerPoints is to design for ease of constructability, which is not to say stop designing really cool looking structures, but just understand the more complex the geometries are, the more challenging it is to install, sheet membranes or fluid applied membranes. There are a lot of products out there, though, that have been developed to address more challenging conditions, but just understand that could be a bit more challenging the more Frank Gehry-esque we design here. So waterproofing system selection, obviously this is an old, long-held tenet, which is no one system for every situation. And the first order of business, as I think I alluded to, is to differentiate between damp proofing, waterproofing, and vapor proofing. So what is damp proofing? Damp proofing is a water-resistant element used in the absence of hydrostatic pressure. Damp proofing products are often a water-based emulsion. Whenever we see the term emulsion, it's basic. Just understand that's suggesting or indicating that this compound is basically in a water suspension compared to, say, a solvent suspension. Damp proofings typically tend to be a class 2 vapor retarder. If anybody's ever reviewed the definitions in chapter 2 with respect to vapor retarder classifications, class 2 vapor retarders are still considered, for all intents, a quote vapor barrier. Damp proofing products pretty much unanimously across the board don't really indicate elongation or tensile properties, and they're not necessarily going to be a guarantee against crack bridging or crack protection. But I always like to suggest that if I had a choice between non-fibered and fibered damp proofings, I would probably lean more towards the fibered damp proofing, because it does incrementally raise the performance level of this type of material. It might help a little bit more towards elevate that crack bridging capability. And the cost difference between it and a non-fibered is, gosh, probably 50 cents, 75 cents a 5-gallon pail. So it's not really a big cost add. So, and I added this recently to this program is the damp proofing is indicated by code, the IBC, where groundwater table is lowered and maintained at an elevation not less than 6 inches below the bottom lowest portion of the foundation or floor, that these floors and walls shall be damp proofed in accordance with this section. So the code does acknowledge that where groundwater levels, i.e. the water table, is below 6 inches or greater below the lowest point of the foundation, that we typically should use a damp proofing. So waterproofing, converse to the damp proofing, is a water resistant element used in the presence of hydrostatic pressure. These typically will have a markedly lower water vapor permeance. These are often going to be, or pretty much uniformly going to be, in a class 1 status, with some exceptions to some of the cold fluid applied waterproofing products out there. But again, these are used in the presence of hydrostatic pressure. I like this image here because it always reminds me of a project we recently wrapped up, the College of Lake County Adult Education Facility in Lake County, Illinois. It's not that an image from that project, but it just sort of looks like it. It was easily probably a 30-foot deep excavation, and this building was approximately about 900 feet from Lake Michigan. And obviously, you're getting that close, you're probably likely going to be in a positive hydrostatic conditions. So all 5 sides of the building's foundation were waterproofed, and a drain tile system was also incorporated with that. So it's just kind of an interesting aspect. Now, there are also other references to where waterproofing should be used. This is an extract from the NRCA, the National Roofing Contractors Association Roofing Waterproofing Manual. They recommend that all interior building slabs below grade in a hydrostatic condition to receive some form of waterproofing treatment. Getting to the code, again, the IBC states that where the groundwater investigation, the geotechnical soils report I was mentioning earlier, indicate a hydrostatic pressure condition exists, the design should not include the design should not include a groundwater control system, such as like a drain tile system, that the walls and floors shall be waterproofed in accordance with this section. A subsurface soil investigation shall be performed to determine whether the existing groundwater table is above or within 5 feet below the elevation of the lowest floor. It's kind of a weird, I'm not sure I understand this after we just read the code passage for damp proofing, which suggests 6 inches or greater below the lowest point of the foundation, damp proofing is acceptable. This one seems to not really make sense, but the fact remains is that the code does suggest waterproofing where we have potential high hydrostatic conditions. So I used to call on the south central portion of the U.S., and I want to back up just a little bit here with respect to damp proofing. One or several firms I recall in Texas who do a lot of design work in that geographic portion of the country told me in no uncertain terms that they don't really ever specify damp proofing, because in those areas where it seems it's relatively arid and dry and not seemingly to get nearly as much precipitation, say as the Pacific Northwest or other areas, that the reason they specify waterproofing is that when they do get the rain or the proverbial monsoons, that the heavy clay packed soil, when it gets wet, it's hard dead packed clay that the ground basically saturates immediately, and the water has virtually no other place to go but up, thus putting their foundations pretty much in a high hydrostatic condition. They can have extremely low groundwater levels, well below the lowest point of the foundation. But the point that they made is that when they do get rain, they get it in earnest, and it creates almost always, according to this one account, creates the positive hydrostatic conditions. So just sort of an interesting thing that we pick up when we travel and make these meetings here. So vaporproofing is any material that's immune to the passage of gas under pressure, and gas can certainly, in our context here, is basically water vapor in the form of a gas. But a lot of these vaporproofing products also serve a second function as a gas barrier, such as gases like radon, probably the most common. These are these typical 10 or 15 mil plastic sheets, and these traditionally have the lowest permeability of any type of membrane sold, with exception to some of the Blindside products we'll talk about here. And these are, well below waterproofing with respect to permeance. Now, one thing I always point out is vaporproofing is not waterproofing. These products are not tested nor recommended for use when we are going to experience high hydrostatic conditions. So I always get a little bit off put when reviewing drawings where both say waterproofing and Blindside are tying into a vaporproofing. I always get a little suspect to that, just knowing how high hydrostatic or conditions react or act in these types of conditions. So just keep that in mind. Low grade systems often will, either these are just the choices that we have here: waterproofing, vaporproofing, drainage, and protection. And drainage and protection courses are pretty much a mandatory requirement. We have to be, cognizant of backfilling operations and the damage that these may cause on our waterproofing, or not necessarily vaporproofing, because those are vaporproofings are typically applied underneath slabs. They're not necessarily wrapped up vertical sides. Typically for slab on grades is where we see our vaporproofing. So the water control system, this just simply speaks to water deflecting or deflection away from structures. Again, as I mentioned earlier, it's always preferred to have grade sloping away from a structure. And certainly our waterproofing should ideally always be tied into some form of drainage, and ideally tied into a drain tile system, aka French drain. Capillary breaks are basically what these drainage mats provide. I wish I could be in person, but I'm restricted to this little camera here. But these, you can sort of see the little cores in between these drainage panel, and that certainly provides that capillary break. And when I talk about grade slope away from structure, this is an example of what I would estimate maybe a quarter 12, maybe even a half 12 pitch slope. This driveway is actually sloping towards this house. This is the end result of a roughly 6-inch rain event that happened in about 7 hours. Actually, we had two of them 2 weeks apart. And I had realized shortly after I'd moved into this house that I had a problem. This was a very warm winter. This was probably March or April of 2017. And the entire front walk, as we can see, is completely submerged. Water was, in fact, all the way right up against the foundation. And so this was not a good scenario. Even the front yard sloped ever so slightly, not nearly as much as the driveway, even though the driveway isn't that much slope towards the house. All it takes is just a little bit of slope, and we can see a pretty considerable accumulation of water. Now, the developer attempted to put a miniature swale, as we can sort of see in the upper right portion of the picture, but that really didn't do anything. And to make matters worse, they decided to drain a good portion of the front roof's elevation into a 4-inch corrugated plastic ABS type of slotted poly pipe, the 500-foot coils everybody's familiar with, wrapped in a sock. And they ran it underneath the front elbow, the bend in the front walk, about 4 feet off of the walk, about 12 inches below the soil, into a 90-degree thin-walled white PVC elbow with one of those friction-fitted slotted ends in, thinking that the heavy clay-packed soil would somehow magically absorb half of 2,500 square feet of rooftop water into the soil. Well, every time it would rain, there would be probably a 12-inch high, 3-foot by 6-foot grass dome that would develop from all the water underneath. And in fact, when I basically hand dug this trench, tied it into a 1 square foot box drain, and when I reached the bend in the front walk is when I discovered that 90-degree elbow from the front walk. And when I unplugged that elbow from the ABS slotted pipe, I unearthed probably about 18 inches of ceramic roof granules that just, unplugged it and all this water rushed out. So it was pretty dramatic. But instead of using that 4-inch ABS pipe, I elected to use the 4-inch SDR 35 pipe that's slotted on only 1/3 of the circumference. The reason being is that I wanted to be able to capture that water and bring it and get it away from the structure. I don't really care for that 4-inch corrugated stuff because it's slotted on 360 degrees of its circumference, and that would just drop a lot of the water right there. Yes, granted, some of the water does find its way out, but if I wanted the most efficient, what I did was basically I used the 4-inch SDR 35 thin wall. And yes, it's more work. You have to dope the elbows and 90s. But what I ended up doing is I dog-legged it here, and then I wrapped the pipe with filter fabric, and then put 3 inches of washed 3/4 inch minimum gravel aggregate on top, and then topped that rock with more fabric, and then replaced the soil and the grass. And the off to the upper right-hand corner of the top image, the grade slopes away from the structure. And this was just a typical average rain event that I managed to capture some of the water just geysering out of this end. So it's taking a lot of that ground surface water runoff along with all the water off the roof. It's pretty dramatic. I've seen some rain events where it was actually geysering up, gosh, probably in excess of 3 feet out of the ground. So I'm taking full advantage of that 4-inch pipe. I switched to solid piping after the bend in the front walk, just to make sure that the water found its way to daylight. So again, my point to all of this is daylight the water, or run it into a stream or a pond or some type of sump pit and get it away from the structure. That's just really the takeaway here. So same house, but nothing to see here. This was a result of a $700 home inspection that did not catch this, if anybody's catching on to this. So yes, it has been since fixed, but I did have one clean and cool kept gas meter, to be sure. So rim shot, please. So to move on to positive side waterproofing, it is simply a water resistive element applied on the immediate or positive side of the water exposure. These types of membranes can be these sheet membranes, the ubiquitous 60 mil self-adhering sheet. These SBS rubberized asphalt. So 56 mils of asphalt bonded to a 4 mil high density polyethylene. Fluid applied membranes, typically the cold fluid applied, are used. Cementitious waterproofing membranes, and these can include the polymer modified cement waterproofings or the topically applied crystallines. And of course, then the accessories are these composite protection boards. It's not uncommon, obviously, to protect waterproofing with either rigid insulation, which can and is pretty much qualified by all manufacturers as a means of protection. But if we want to really do the system correct, then we'll also add a geotextile drainage mat, aka drain board, on top of that. Now I'll get into that here in just a moment. So negative side waterproofing is a water resistant element applied to the opposite or negative side of the water exposure, i.e. this would be the interior side of a basement foundation. And probably once every year or so, we get an inquiry where someone says and is asking if we have any type of coating or waterproofing that they could apply to the interior side of their basements. And it's just plain a bad idea. I think many have probably seen how some homeowners, for example, or maybe some commercial property owners would paint their interior side of their basement foundations. I would posit that many of those are probably have it at the bare minimum, or at the most, frankly, damp proofing, which eventually is again, damp proofing is really the lowest common denominator. But we've seen examples where the paint eventually starts to alligator crack, because again, the 100% RH source on the outside is going to move through that concrete, which may not have as low a permeance as the aforementioned waterproofing, or for that matter, damp proofing, and delamination as a result. Now, there are products that can be used in these types of conditions, but these are pretty much solely going to be a Portland cement based type of material. we all know as crystalline waterproofings, or the slightly higher performing polymer modified cement waterproofings, which, as their name implies, have a nominal amount of acrylic polymers in them. And I'm holding this up to the camera. This is a sample of it, but these do have a ability to flex and move a little bit, which, but it is still going to be limited. But I always like to point out that when considering the application of these crystalline or polymer modified cement waterproofings require that the surface has to be opened up through high pressure water jetting or sandblasting, and that's a pretty disruptive operation, especially if the building is maintaining occupancy. If it's a pre-existing structure, if it's new construction, it's probably less of a concern to have to deal with water or cleanup of the sand from the media blasting. We want to, achieve a CSP typically of 3 or 4 minimum to provide that mechanical bond, as we'll discuss a little bit further in. So material selections, waterproofing, we have to consider their service life. Do we want the, just the lowest common denominator, damp proofing, which really doesn't come with any type of warranty short of, say, a 12-month material only warranty? Cost, substrate conditions, peripheral material compatibility. Are we using a silicone air barrier above grade and tying it into an asphaltic, foundation waterproofing, which is a big no-no? Extreme cold or heat application, complexity of use, ease of application, the credibility of the manufacturer, how long have they been at it, what type of warranty schedules do they offer? All these have to be obviously considered. Sheet membranes, fluid applied, cementitious, conventional blindside application. Self-adhering membranes, these were developed in 1972. These 60 mil self-adhering sheets, these are specified typically in 07-13-26. As I mentioned, there are 56 mils of SPS rubberized asphalt, basically cured, hot fluid applied, bonded to a 4 mil carrier film. And far and away, I would probably guess that these are the majority of the waterproofing types. This is the majority of waterproofing type used. I'd say I'm probably better than 50% of projects out there. It's portable, and it can be applied in vertical or horizontal. If you use a water-based primer, which it is required, it's not really going to be a nasty operation, and typical for horizontal and vertical uses. Fluid applied membranes come in really three flavors. Hot fluid applied, these have been in existence for about 65 years. Cold fluid applieds, I would say that the majority of this type falls into the category of a modified polyurethane or modified urethane type system. And then we get into these quote resin type systems, PMMAs and PUMAs. And I present this PowerPoint a lot. It's interesting that a lot of people are still really unfamiliar with these types of systems, even though PMMAs were developed, I believe, in the mid to late 1960s, and their newer version, the PUMAs, were developed roughly about 25 years ago. This stands for polymethyl methacrylate, or the PUMA is a polyurethane methyl methacrylate, but running from least to most expensive are obviously the hot. Hot's always going to be my go-to for horizontal applications, although I've had a few projects over the last 15-20 years where we specified it for both horizontal and vertical. If somebody wanted the absolute best and the lowest permeate type system, that's really the way to go. But obviously for vertical, we commonly will consider a cold fluid applied. SPS, the hot system, again, is a SPS rubberized asphalt, styrene, butadiene, styrene, and really we're not really at all restricted by minimum application temperatures. This is 356 to 392 degrees. Pretty much we just refer to it as 400-degree asphalt. It's a 215 mil 2-ply reinforced system, which basically has no seams. And its primary uses, most notably, are green roofing, plaza decks, and split slab garage slab type decks. But these systems manufacturers require authorized installers. One of the big points of often contention is that the concrete they're applied to, we can certainly apply this over cement board and plywood, certainly, but the The concrete has to be aged. Typically, we specify 28 days, 14 days on the absolute minimum. I would say also that lightweight structural concrete is possible, but lightweight structural, and I'm emphasizing the word structural, requires a minimum 60-day cure time. Lightweight non-structural concrete is certainly off the table. We simply can't. It's too friable a material to gain any type of good mechanical and adhesive bond to. The cold fluid applieds are mostly going to be a single component, although there are some two components, and the two component products out there, in my opinion, are some of the most tremendous materials. But a lot of contractors want, convenience and just go with a single component. But the two components, I think, are more often used more as an accessory flashing, but they're certainly available to be used as a waterproofing. These are, again, polymer modified, usually a modified urethane type material, and referred to as moisture cure. The term moisture cure simply suggests that these membranes actually benefit from a little bit of atmospheric moisture. One of their big benefits compared to the hot system is that they can be applied to green concrete, usually no sooner than about 3 days after removal of forms, which we can't really say about the hot fluid applied, but we are limited to 32 degrees and rising. So they will be problematic in colder weather application. Both these hot and cold fluid applieds carry the same type of warranty duration. They can be eligible for warranties up to 20 years for both the hot and the cold fluid applied. Blindside systems, these are used for under slab conditions, zero lot line conditions. We had a project years ago, about 15,000, 20,000 square foot facility for Airbus, pretty much on the Gulf of Mexico. They went down about 15 feet below grade for this project, but these are usually either a mechanically bonded through a fleece back type material or adhesive chemical bond. And these are often tied into, if we use these for under slab conditions, these will be used to tie into a self-adhering sheet or post-applied waterproofing if we have freestanding vertical walls. If we have zero lot line conditions, very often we'll use these to pre-apply on the exposed bottom of the foundation and then attach them to the wood lagging or sheet pile systems for again, a very, very close quartered type of application. So these are, again, as I mentioned, they're either mechanical bond or chemical bond to the concrete, depending on the manufacturer's design of the membrane. And very often these will be used in conjunction with a drainage mat. So the drainage mat is always going to be on the outside of the application. So if we're applying up against a wood lagging or sheet pile, we'll have our drainage mat applied, and we typically pin it at the very top of the lagging, and then just drape it down. And then the blind side is going to be facing the concrete when the concrete gets placed up against it. So bentonite sheets are also another form of waterproofing, and I think there are a lot of different approaches to this. This one I'm holding up here, I wish, again, I hope this is visible, but this is a composite sheet which has a 20 mil high density polyethylene backing film bonded to some bentonite clay fibers. And the bentonite clay fibers are always going to be facing the structure. I typically like to recommend these types of systems for stone and mortar foundations. We're currently doing a project in Michigan where the Edsel Ford house, there's an underground tunnel leading from the garage to the main house that it needs to be re-waterproofed. And it was waterproofed, probably 100 plus years ago with coal tar pitch, as we believe it to be. And one of the contractors came up with a brilliant solution. Instead of removing the coal tar, why not consider going with a bentonite sheet? And we can just basically encapsulate the coal tar, which is really nasty and very expensive to remove. It's an environmental hazard to remove it. But these systems can certainly be used for blindside and pretty much any of the applications that we've talked about thus far. But it is a mechanically fastened system, so we need to fasten it to viable portions of a structure. Period foundations are one of my go-tos for using this type of system. Now, one of the cons might be is that if they're partially installed and then the a job site gets exposed to a heavy rain event, this bentonite clay will basically will hydrate and often can ruin the material before we've had a chance to backfill the operation. We've actually had that happen, unfortunately, on one or more occasions. And so it's something that has to be considered when factoring into what type of systems to use. So sheet membranes, high density polyethylene is just the carrier film that we use with these pressure sensitive adhesives and weather resistant coatings. Bituminous membranes that incorporate the embedment of the membrane in the concrete as it pours, contains these nylon fibers. We're talking about the Blindside here, so the means of mechanical attachment. And certainly we always want to make sure that manufacturers standard installation guidelines are followed here. Difficult details, we're showing a number of different conditions here where we have pipe clusters very close together. I'm a big proponent for referencing NRCA guidelines, this roofing and waterproofing manual. Pardon me, if anybody's not familiar with it, it does advocate, and this is probably very wishful thinking on my part, but they advocate to have a pipe have pipe penetrations spaced a minimum of 12 inches apart. This way, their position is that it allows the installer to properly flash the flashing around the pipe without any encumbrances. We typically flash a pipe, whether it's a below grade foundation or a roof vent stack, pretty much in the same manner. We have 3 inches of the flashing onto the substrate and 3 inches onto the pipe penetration. Now, I realize, again, I say that's wishful thinking. It's often it's not possible where unfortunately, we're faced with having to cluster pipes ever closer together. And in many cases, they're actually touching each other. The problem I have with that is, if we treat it like a pitch pan, and a number of us manufacturers can and do accept a pitch pan using a heavy bodied mastic around the pipes to effectively waterproof them. If the pipes are touching each other, are we going to be 100% sure that mastic is basically providing or creating a seal in between the two pipes where they're virtually touching each other? That's anyone's guess. And I'm always getting a little bit leery of those types of conditions. One workaround, a project I was involved in years ago, where the modern wing of the Art Institute of Chicago was built, a bridge over Monroe Street from the museum into Millennium Park was built, and the general construction manager, Turner Construction, unearthed a giant vault similar to this image in the lower right. This is not from that project, but this always reminds me of that condition. Unfortunately, Turner didn't have any information on their drawings as to what all of this battery of utilities was going to. But, rather than to waterproof around all of these pipes, they basically created a giant vault around it. And it's a lot easier to waterproof a right angle, a 90-degree corner, as opposed to try to waterproof around all of these penetrations. So just, this waterproofing principles, the first principle, 91% principle, most of the leaks result from 1% of the envelope's total surface area, and 99% of leaks are attributed to causes other than the material or material failures. So some of these conditions, again, designed for constructability or ease of constructability, is something I always had stammer on about. So think ahead. Consider how waterproofing systems will interface with other elements. This was a project that did have a Blindside or an underslab waterproofing system specified. Unfortunately, there was no coordination. I can only presume that the pre-construction meeting did not have the waterproofer and the electrical contractor discussing each other when each were going to execute their work. We've got all these Schedule 80s and Unistrut. If we're going to terminate our Blindside or underslab system around the column, we've got all that Unistrut in the way. So it was not a good situation. So as we mentioned, we always want to protect the membrane, and the protection boards, protection sheets, protection courses are, just as their name implies, are designed to protect the waterproofing system while the trades continue the rest of the work, whether directly of the waterproofing or some of the other, mechanical trades getting in. And once a horizontal waterproofing's been installed, it has to go through a membrane integrity check, i.e. a leak detection. And there are really two methods. And the flood method has long been used, where we flood with a 2-inch head of water. We block all the drains and scuppers and fill it with 2 inches of water, let it sit for 24 hours, have the manufacturer's rep come back and then examine and sign off on it. But if there are any leaks in a flood test, the leak can propose some water. And once that water gets on the underside, it can traverse laterally in any number of directions. And it's going to be a lot more difficult and more time consuming to find that leak, that breach. Compare that to the electronic leak detection we see here on the right, where all we need to do is basically put a low voltage 600 volt locate wire on the periphery, run it to all the drains, and just apply a thin film of water. We basically use the concrete deck with the embedded steel to create a negative condition underneath the membrane, and then we positively charge a low voltage signal on top of the waterproofing through the thin film of water. And then a leak detector with these voltage indicators simply traverses the deck, much like you're cutting the lawn. And when they find a spike in the current, an audible chime will come up on that thing that's around this guy's neck, and he'll be pretty much right on top of the breach. And it's a lot easier to locate the leak at that point and effect the repair. So it's a lot faster. Time is money, as opposed to having to do the flood test. And when I started at this, there was only one organization in all of North America. Now there are electronic leak detectors almost in every major and minor metro area. So it is fast becoming pretty much the default. And they also use a high voltage non-water wet method for vertical surfaces for leak detection. So we actually use this on a project in Wisconsin. It's probably about 14 years ago now. And prefabricated drainage layers. These are systems that are used for multiple purposes. They're used to protect the waterproofing, but also, more importantly, they reduce the hydrostatic pressure on the system, and they might also extend a warranty. These are always a good thing, and I always bring up the question that I suspect will be for the ages. We get this question almost every other month: is where do we as the manufacturer advise placing the drainage mat relative to the foundation insulation? A lot of contractors seem to, because this is in a sheet form, if we're using a sheet waterproofing, we're going to apply the sheet waterproofing on the foundation and then place our sheet drainage on top of the waterproofing, and then cover it up with the insulation. And, us as one manufacturer, our details will show the reverse of that. We have the waterproofing on the foundation, we then insulate it, and then we apply the drainage mat on the outboard side of the insulation. And the reason for this is that the drainage mat has an inbuilt fabric, a filter fabric, to prevent fines from the soil from getting into and clogging the drainage core. Secondarily is if we place the drainage mat behind the insulation, how much water is that drainage mat really going to, quote, see? It's not going to see a whole lot. If we place the drainage mat on the outboard side of the insulation, it places it in closer proximity to the atmosphere. And like, I'm dating myself here, but the big old cans of the tin cans of 32-ounce high C punch, or in fact, 70 years ago when beer was sold in cans where you had to use a can opener, you'd have to actually pierce both sides of the top of the can, opposite sides. So as you poured the liquid out, air would go in and displace the liquid that was going out. It's going to provide more efficient drainage. And another point could be is if we place the drainage mat on the outboard side, it's a lot easier to integrate or incorporate this with the drain tile system below it. If we go between the insulation and the waterproofing, it makes for a little bit more challenging application. Now, consider in a waterproof horizontal deck, there's a particular manufacturer of extruded polystyrene that makes the familiar blue stuff their warranty position will not be honored for thermal warranty of their insulation if a drainage mat factors underneath the insulation. There's a technical bulletin I have a copy of if anybody's interested in that. So I could go on and on and on about this, but keep in mind where, at the end of the day, there's no, the waterproofing warranty will still be eligible irrespective of where the drainage mat figures. But I'm just pointing out some pros to place it on the exterior side of the insulation layer. We also advise that the project engineer or landscape architect, whomever is involved in choosing the drainage mat, should really choose the drainage mat based on the compressive strength, the flow rate characteristic of both the sieve rate of the fabric, as well as the flow rate in gallons per minute of the core, because we as a manufacturer aren't really going to know, what conditions exist on each project as we get involved with them. So all the data sheets will show the compressive strength and the flow rate characteristics as what we talked about here. Cementitious waterproofing, the crystallines we talked about. Again, these topically applied. There are also admixtures. The admixtures that are cast with the concrete. This is really looking at the topically applied. That what they do is they combine with the free line that's pre-existing in concrete and reinitiate the crystalline growths, thereby reducing the capillaries or pores within the concrete. Now, obviously, since crystallines are largely a Portland-based material, they are very stiff. So if there is any substantial movement with this type of waterproofing, all bets are off. But a lot of times we'll see crystallines or topically applied or the polymer modified cement waterproofings used in conjunction with a sheet or fluid applied waterproofing as a proverbial belt and suspenders type of approach. Very commonly, we'll see these almost ubiquitously in elevator shafts. If a elevator shaft is cast and no underslab or vertical foundation waterproofing on the exterior was considered or used, we can certainly apply this to the interior side of that elevator shaft. Below grade parking decks are another very common application. Wastewater containment facilities are probably our biggest use of these types of systems. And again, they're spray applied or they can be trowel applied. Bigger projects obviously make better use of spray applications. But I talked about that flexible cementitious, the polymer modified cement waterproofings. But bear in mind, again, the substrate has to be opened up as we see in this image here. And that can be a pretty destructive operation if it's a pre-existing structure. There are several options. Again, high pressure water jetting or sandblasting. So running out of time here, but below grade gas retarders, again, these are only used for mitigating water vapor transfer or brownfield site developments. Sometimes we have, brownfield sites where they have BTEX chemicals, and we'll go with the more substantial 7-layer chemical resistant types. And also a little spec note here when specifying these types of systems, when we specify the plastic ones, we always use the ASTM E1745. E1993 is the standard spec for bituminous vapor retarders. So just know that there's a difference there. And we're just also referencing the ACI guidelines for below grade slab preparation to receive these types of membranes, which are also the same standards we use for the Blindside waterproofing system placements. So just some quick snapshots of these systems going down, and pay particular attention to the penetrations. Yes, these systems can also be used in conjunction with an active radon mitigation system, i.e. a 24-hour day running fan system to create a negative pressure underneath the slab. But these systems have to be, they're most commonly made of virgin resins as opposed to reclaimed, recycled, which the virgin resins are going to be much more durable for withstanding the rigors of concrete placement and the trades on top of them. So anyway, to close out here, we just want to consider waterproofing based on owner and project requirements. Design and installation details are very, very important. The more complex the design, the more challenging the installation. And by all means, enlist the manufacturer's technical rep reps to help you guys with the specs and drawing development. That's what they're there for. As early in the design process as possible would be great. And certainly discussion of during pre-construction meetings, as we talked about those conditions that unfortunately befell us on a couple of projects, but that's really the onus of the GC or the CM. So quick 15-second commercial on WR Meadows here, since we're done with the AI portion. Seal mastic emulsion. We also have a solvent-based bituminous damp proofing. Precon is our Blindside waterproofing. Melroll, that's our 60 mil sheet waterproofing. HR 714 is our hot applied rubberized asphalt waterproofing, which we use for our green roofing systems, split slabs, and plaza decks. And Hydrolastic 836 and its cousin 836 SL. We also have a newly added product called Vertibarrier NS, which is sort of a vertical applied, non-slumping type of cold food applied. And then our Adicon and Semcoat lines for our polymer modified cement waterproofing and crystallines. And with that, I'm gonna close it out here. I do have a quick reference sheet here if anybody needs it, sort of a specifier cheat sheet. All our products listed by spec number and title, with a minimum of 2 competing manufacturers in each spec category.
Thank you all for your time and attention today, and have a great day. Take care.